All right. Wicked electric field packet. For field lines with the correct orientation between charged parallel plates on the left. All right, so I'll do this in red. If you put a little test charge in there, which way does it go? It goes away from the positives and towards the negatives, so my field lines would go like this, with arrows pointing to the right, making them as parallel as possible, though I really didn't do a good job of that. They're parallel, but they should be equidistant to represent a uniform electric field. And let's say you were an electron. So let's say I'm a little electron and I'm all the way over here. As I go through here, according to E equals F over Q, the definition of electric field is like the force felt per charge in it. This is going to feel a force making that electron go opposite the direction of the field lines. So it's going to kind of start to hook like this. Kind of like that. Going to be repelled from the negatives on the right, attracted to the ones on the left. Well, it's kind of like gravity. It's a constant force in that direction, so you're going to see the path start to go, parabolic. If you were a proton, let's put him on this side, then you would take the opposite path. And a neutron, which is neutral, we'll put him right in the middle, unaffected, because he has no charge. Poor little neutron has no charge. That's a country song right there. 2 charges of 25 microcoulombs are set far apart. Calculate this for, okay, so it's just a plug and chug thing. Fe equals K Q1 Q2 over R squared. So it's going to be 9 10 to the ninth times 25 microcoulombs. Well, micro is 10 to the minus sixth. So that's going to be 25 times 10 to the minus sixth times itself. So I'm just going to square it. Divided by 0.025 meters squared. That comes out to, if I did my math right, 9,000 newtons. It's a lot of force. 2 electrons. Where do I find a charge on an electron? Page 1 of the reference sheet. Where are we? Electron volt. Charge on electrons right there. I think you also get the mass of I get a mass of an electron right over here. All that good stuff. Mass of proton, mass of neutron. So 2 electrons are held that far apart. 1 on the left and 1 on the right. Calculate the electrostatic force between them. Okay, so it's K, 9 times 10 to the ninth, times the charge on one electron, which would be negative 1.6 times 10 to the minus 19th. Just square it because the other one's the same, Q2, divided by 0.25 squared. That comes out to 3.68 times 10 to the minus 27th newtons, if I did my math correctly. All right, that's the force on it. Using F equals ma and neglecting gravity, find the initial acceleration of the right electron if the left is held stationary. So one gets let go. Remember, it takes 2 things to make one force. They both feel it. So I'm going to use F equals ma. Force was 3.68 times 10 to the minus 27 equals the mass, which I'm going to look up, 9.11 10 to the minus 20, wait, 10 to the minus 31. Kilograms, that's the mass of an electron, times A, divide over. What do you get? Let me see, I wrote this down somewhere. A big number. A equals 46.5 meters per second squared. That's a heck of an acceleration. Where are we now? Okay, use this and that. Find the electric field intensity at the position of the right electron due to the presence of the left electron. So it's basically the electric field due to that one electron. It's very specific. So E equals, when you put this, sub this into there, 1Q goes away, KQ over R squared equals 9 times 10 to the 9th. And again, I'm going to leave the negatives out of here because they don't really have good meaning for us. It could confuse us as to what direction things are going in. 1.6 times 10 to the minus 19th, because it's a charge on one electron, divided by the distance away. Oh, it's referring back to this question, which was 0.25 meters. Gives me an electric field intensity of 2.3 times 10 to the negative 8th newtons per coulomb. Right? Electric field is also force per charge, newtons per coulomb. Now find the electrical potential, the voltage. Well, that is work over charge. Work is force times distance over charge. Plug F in. You're going to get rid of one distance and one charge, leaving you with KQ over R. So we get 9 times 10 to the 9th times 1.6 times 10 to the minus 19th divided by, I'm way too enthusiastic with this, 0.25. That's giving me a voltage, electrical potential, potential difference, three ways to say the same thing, of about 5.76 times 10 to the minus 9th volts, capital V for volts. How much energy does the right electron have due to the presence of the left? So it's the stored energy of it. Well, since your electrical potential, which we just calculated, equals the work done per charge or the stored energy it has, because it's sitting there, I just got to solve that for PE. Voltage times charge, so I'd have 5.76 times 10 to the minus 9th volts times the charge on an electron. And again, I'm not going to include the sign. 1.6 times 10 to the minus 19th coulombs, which gives us a little tiny bit of energy of 9.216 times 10 to the minus 28th joules. Not a whole heck of a lot. There's page 1. Page 2. I should probably put on some lights. There we go. Looking at a pair of parallel plates. This is the beginning part of that old school TV tube I showed you guys. It's actually called the electron gun. It's about how you shoot an electron and get it up to speed so it can make an old school TV work. Two large parallel plates. This is D apart. Okay, they are distance D apart. That is distance from here to there. That's D. Equal charge at Q, but with opposite polarities by a power source. potential V, there's a vote. Right away I know I can figure out now in terms of D and V what the electric field intensity is. It's just V over D. And electric field from E. So I've got a particle of mass m charged negative q, released from rest of the cathode. Use the correct situational equality to prove. Okay. Force felt by the charge is that. Well, it gave me enough to figure out what the electric field intensity was, which is V over D. And it's bringing in a Q and an F. So electric field also equals force felt per charge. So if I just multiply over by Q, therefore F would be Q times V, V times Q over D. All right, work done moving the charge. Well, is W equals QED. Okay. Well, we're going to have to do something with voltage because by definition, your potential difference, the voltage, is the work done per charge. Nope. Damn, that's an ugly looking Q. Sorry. I'm solving for W. Therefore, W equals voltage times charge. All right. Got to get rid of V. Well, if you look at the formula right up here, E equals V over D. Therefore, V equals E times D. So I could take out V and get E D Q. Looks better this way, QED, but same thing. Last one down here says, the speed of the particle as it leaves a positive plate could be, well, I just solved for work. And my train of thought here is, work and energy, just same stuff. I start seeing things like V equals a square root and a 2 in it. I start thinking about kinetic energy of 1/2 mv squared. You know, when you take the square root of V, you get the square root of the other side. The 1/2 gives a 2. That's what leads me to do this. So let's set what we just had because it already expressed work or energy in terms of E, D, and Q. And I'm seeing E, D, and Q. So let's use it. Since work is the same as energy, and this thing said ignore effects of gravity somewhere, I think. It's just going straight across. It's not getting any gain in potential energy due to height off the ground. It's getting a total gain in kinetic energy. So I'm going to set 1/2 mv squared, which is the change in energy, starts from rest, shoots across, equal to that EDQ. And solve for V. Multiply by 2, divide by m, take the square root. E is going to be the square root of, multiply by 2, 2EDQ, divide by m, and take the square root, and there we go. And another way to express the same thing. Mass is still in my denominator. 2 is still there. Q is there. Let's get rid of V and bring in ED. Well, since E equals V over D, V must equal ED. So I can plug in for ED here, V, and you got that. Done like dinner. This is your basics of a TV. You have your electron gun over here. Shoots this thing up, gets it up to a certain speed. Then we have plates over here that are going to make electric fields. And just like we did on page 1, charged particles will bend in electric fields, and that's how you do your vertical and your horizontal. Your parents will get this controls on the old school TV so that the electrons hit where they're supposed to hit. Those two sets of parallel plates to the right. Okay, that's what's going to happen. If that's positive, that's negative, and we're firing electrons, then as the electrons are brought up to speed by this part of it, which is what we just figured out on the last page, kind of showed how that worked, goes shooting through here. It's going to be pushed up by that negative plate while being attracted to that positive plate. Then when it gets into this part, that's a positive. I can't draw it, but it's going to be pulled from that side kind of over to this side. Force between 2-point charges is 5 newtons. So 5 equals, okay, this is the double this, half that thing. So you get 5 when you put in K Q1 Q2 over R squared. Let's change what they say to change on the right. One charge is doubled. I'm going to double that guy. Now I've got to double this guy. The other is tripled. I got to triple this guy. Now I got to triple all this. Distance between them is reduced by 1/3. That gets divided by 3. That means this gets divided by 9. So 25, no, I may have 3%. 5 times 2 is 10, 10 is 30, 30 over 9. That would be the answer. Oh, man. All right, my screen went dark. I thought I stopped recording right in the middle. I think I'll save this guy for another day. Yeah, we'll do it in halves. That's the part we'll go over tomorrow.